Hi, this is John Whitaker for the Mathematical Analysis 2 class, and this is our first, it's our first video lecture for this term. And we want to start in chapter 5 of our text, which has to do with differentiation. And I want to begin by saying that we will mostly consider functions defined on intervals A to B, or segments, open intervals from A to B, of real numbers. And as it's written there, that's the type of functions we're going to differentiate mostly. So what is the derivative? Okay. So, as a definition, if we let f be defined and be real value, on the closed interval from A to B, then for any x in A to B, form the quotient we call it phi of t, given by f of t minus f of x all over t minus x. And here we're thinking that t is between A and B, and t is different from x. And define f prime of x to be equal to the limit as t goes to x of phi of t, provided this limit exists. And of course, this limit, or f prime of x, is the derivative of f at x. So f prime of x is known as the derivative of f of t at x. And so that definition had to do with a limit. And with this being our first lecture and having done analysis 1, might be a good time that this limit definition leads us to review some important aspects from analysis 1. So let's go back and recall. First, the definition. A set X whose elements we should call points. Is said to be a metric space if with any 2 points let's say P and Q of X, there is an associated real number that real number we represent d of P comma Q, called the distance from P to Q, such that, okay, so what does this d satisfy? The first thing is that d of PQ is always greater than 0 if P is different than Q, and the distance between P and P equals to 0. B, the distance between P and Q is the same thing as the distance between Q and P. And part C, the distance between P and Q is less than or equal to the distance between P and R plus the distance between R and Q, and this is for each R element of X. So that's what we meant by a metric space. And we had learned that in chapter 2 of our text. And let's not forget, any function which satisfies the 3 previous properties is called a metric. I'll say on X. Distance function. Okay. Another definition I'd like to recall is that we let X be a metric space. Then we can have a few definitions here. First definition, a neighborhood of P, element of X, is a set N sub R of P which is contained in X, the metric space, consisting of all points we'll give those points names. We'll call them Q. Q, such that the distance between P and Q is less than R for some R greater than 0. The number R is called the radius of this neighborhood of P. Another definition, topological definition to solve in chapter 2, is that of a limit point. So a point P is the limit point of the set P that's a subset of our metric space X if every neighborhood of P contains a point Q where Q is different than P and Q is an element of E. That's what it means for P to be a limit point of E. Okay, so as an example, consider the set of real numbers with the usual metric. Absolute value between the distance. The absolute value of x minus y, I should say, where x and y are real numbers. Then, if you look at the neighborhood radius 1/2 center to 0, that's equal to minus 1/2 to positive 1/2. And if E is equal to the set of all real numbers that have the form 1 over n, where n runs from 1 to infinity, okay, which is equal to 1, 1/2, 1/3, 1/4, and so on, then zero is a limit point of E, but 1 is not a limit point of E. A third definition I want you to recall is the following. If we let x and y be metric spaces, and we suppose E is a subset of x, and that a function f maps E into y. And P is a limit point of E. Then we write f, let's say, of x goes to Q as x goes to P, or the limit as x goes to P of f of x equals Q, if there is a point Q, if there exists a Q element of y with the following. That is, for each epsilon greater than 0, there exists a delta bigger than 0, such that for all x in big X with it's not in big X, it's all x in E. Excuse me. With 0 less than the distance between x and p being less than delta, then the distance between f of x and q will be less than epsilon. Okay? And so that's the definition of a limit of a function. And since this chapter has to do with continuity, we're going to primarily be talking about real value function here. So let's look at an example here of the limit of a real value function. So let's show that the limit as x goes to 3 of minus 2x plus 5 equals to minus 1, where we're considering f of x as our function. Let me write down this x like that. F of x is our function to be equal to minus 2x plus 5. And big X, the metric space, is the real numbers. And y is also the set of real numbers. And the metric on x is the usual metric on the real numbers, that is between x and y, or p and q, if you will. The distance between p and q is equal to absolute value p minus q. And the metric on y between, let's say, two real numbers w and z is equal again to absolute value w minus z. And we're going to let E be equal to R as well, because that's what f of x is defined on. Okay, so we want to prove this limit is minus 1. Okay? So here's the proof. We let epsilon be greater than 0 be given. We need a delta bigger than 0 such that for all x element of R with zero less than the absolute value of x minus, what p is in this case is 3. Whenever that's less than delta, then that's going to force f of x, which is minus 2x minus 5, minus the q, which is minus 1, to be less than epsilon. So we want this to happen. So we want minus 2x, I think this is minus 5 plus 1, so that's minus 4 to be less than epsilon. This should have been a plus 5. I made a mistake. I didn't look at f of x very well. So here, this is plus 5, that's 6. So it's plus 6. So this is what we want. I made a mistake. So we want minus 2 times the quantity x minus 3 to be less than epsilon. That means we want the absolute value of minus 2 times the absolute value of x minus 3 to be less than epsilon. That means we want x minus 3 inside absolute values to be less than epsilon over 2. We're dividing by the absolute value of minus 2, which is just 2. So in order to ensure that happens, we're just going to let delta be epsilon over 2. Okay? And that's the delta that will work, and you just work backwards, which I'm not requiring for the proofs here. And this is a prototypical problem that we would have seen from chapter 4. Okay? The fourth thing, so I'm going to call that in. The fourth thing that I'd like to recall is a fact. And it says, suppose E is a subset of X, which is a metric space. P is a limit point of E. F and G are complex functions on E, and we have two things. The limit as maybe x goes to P of f of x equals to A, and the limit as x goes to P of g of x equals to B. Then we have three things we can say. The first is the limit as x goes to P of f plus g acting on x will be equal to A plus B. And as a reminder, what that says is the limit of a sum is the sum of the limits, because limit of f of x is A and limit of g of x is B. And we could really write this as plus or minus, so whichever is involved there. Part B, the limit as x goes to p of f times g, acting on x is equal to a times b. And part C, the limit as x goes to p of f divided by g is equal to a divided by b, and that's provided b is different than 0. And g of x is not 0 on you. So that was something that we had previously, a fact. Okay? And that was from chapter 4. Algebraic properties of limits. Again, it's good to have a review of what we've done in analysis 1, and it's also being prompted by our definition for a derivative. Another fact I'd like to review is not a fact, but rather a definition. It says, suppose x and y are metric spaces. E is a subset of x. P is an element of A. Okay. Let's say, not A, but rather E. And F maps E into Y. Okay. Then F is said to be continuous at P if for each epsilon greater than 0 there exists a delta greater than 0 such that the distance in y between f of x and f of p is less than epsilon when, or for all x I should say, element of E with the distance in the metric space x between x and p is less than delta. Okay. So this is also a definition from chapter 4, that of continuity. Okay. So as an example, we have f of x is equal to 3x plus 7, where we're thinking of this is, let's say, continuous at x equal to 2. And here we're thinking of f goes from R into R. This is x, y, or E and y. And the metric on x between x and y is equal to that, the difference in absolute phase between these 2 points. And similarly, the metric on y, which is also R, between y and z, is going to be equal to the difference inside absolute phase between these 2 numbers. And so here's the proof. and works extremely similar to the proof where we had earlier of the example of the limit of a function. And so here we let epsilon be greater than 0 be given. What we're looking for is a delta. That's this distance. It's greater than 0 such that for all x in here R with x minus, and here I want to put down p, and that p is 2, being less than delta, then that's going to force the distance between the output values, which are f of x minus f of 2 to be less than epsilon. So what we want is this distance. Well, f of x is 3x plus 7 minus f of 2. So when I stick in 2, I get 13. We want that to be less than epsilon. So what we want, we don't have it, but this is what we want. We want 3x minus 6 inside absolute values to be less than epsilon. Oops. So what we want is that the absolute value of 3 times the quantity, it's x minus 2, to be less than epsilon. So we want the absolute value of 3 times the absolute value of x minus 2 to be less than epsilon. So we want absolute value of x minus 2 to be less than epsilon of 3. So we let delta, that's what we get to control, be equal to epsilon over 3. And then you work backwards, but I'm not going to be requiring that. That's good enough in this case. And then the final thing that I'd like to review, the sixth thing, is the fact, and it says let x and y be metric spaces and E be a subset of X. We let F map E into Y and P be a limit point of E. As well as being in E. Then F is continuous at P if and only if F of P equals to the limit as x goes to P of f of x. So that's something that we had proven in chapter 4. Okay. So let us recall, we remember that the very first thing we did for this term in terms of the definition, is that f prime of x is equal to the limit as t goes to x of f of t minus f of x all over t minus x. So that's the definition, the derivative of a function at x. Okay? So let's look at an example. And let's let f map 1 to 7 into R be defined by f of x is equal to 3x squared minus 5. Then, here's what we're playing. F prime of 2 is equal to 12. And again, we're going to use the usual metrics. That is, on real numbers, the metric on x, x comma y, that's the value between the difference between x and y, and the metric on the output space, which is also R, between 2 points, 2 real values, w and z, that's equal to w, that's the value of w minus z. Okay. Well, let's note the phi of t, which is equal to f of t minus f of x all over t minus x would be equal to, so that's the f of t that's here, okay? That's equal to 3 times t squared minus 5 minus the quantity 3x squared minus 5 all over t minus x. Okay, let's see if we can simplify that sum. Well, that's equal to 3t squared minus 5 minus 3x squared plus 5 over t minus x, which is equal to 3 times t squared minus x squared over t minus x. As we can see that the 5's cancel, and then what we have is 3t squared minus 3x squared, and then we factor out 3. And it turns out that the top can factor in even further. It's t minus x times t plus x over t minus x, which will be equal to 3 times t plus x, where x is, where t is different from x, that stipulation. Okay? So, f prime of 2 is equal to the limit as t goes to 2 of phi of t, which is just the limit as t goes to 2 of 3 times t plus here it was 2. Okay, that's what x is. Which this is going to be equal to, this is going to be 4, it's going to be equal to 12. And so, well, let me go through this a little bit more rigorously. Now, what I'll do is I'll prove it. Claim the limit as t goes to 2 of 3 times t plus 2 equals to 12. So this is a limit, so how do we do this in terms of proving it? Well, we use the definition of the limit. And we just reviewed that. So here's the proof of claim. We let epsilon be greater than 0 be given. What we're looking for, this is for a limit. We need a delta bigger than 0 such that for all x element, I think it's from 1 to 7. Sorry, for all t, is what I should say. Element 1 to 7 with 0 less than absolute value of t minus, and here it's 2 less than delta, then the absolute value of 3 times t plus 2 minus 12 will be less than epsilon. So what we want is 3t plus 6 minus 12 to be less than epsilon. That is, we want the absolute value of 3t plus, minus 6 to be less than epsilon. That is, we want 3 times t minus 2 to be less than epsilon. So we want the absolute value of 3 times the absolute value of t minus 2 to be less than epsilon. So we want t minus 2 inside absolute value to be less than epsilon of 3. So we let delta be equal to epsilon over 3. And that does it. It's a conclusionary statement. So f prime of 2, which equals to the limit as t goes to 2, of 3 times t plus 2 will equal to 12. This right here ends the proof of claim, okay? I'll put a little box there. This ends the proof that f prime of 2 in this case is equal to 12. I'd like to look at one more example, and this is where the derivative won't exist because the limit doesn't exist. So when we talk about taking the derivative of a function at a point, because it's a limit, it may not exist. Here's such an example. So we're going to let f of x be defined to be 0 if x is greater than or equal to 0, and minus 1 if x is less than 0. And here's what we claim. Then f prime of 0 does not exist. And so we want to prove that. And we'll prove it by contradiction. So here, let's suppose f prime of 0 exists. So suppose f prime of 0 equals to some real number. Let's call it L. Okay. Okay. So that means that L is equal to the limit as t goes to 0 of f of t minus f of 0 all over t minus 0, which is equal to the limit as t goes to 0 of f of t. And f of 0 was defined to be 0 all over t, which equals to the limit as t goes to 0 of f of t over t. So that's what L is. It's that limit. since that's what L is, then if we let epsilon be greater than 0 be given, so L is that limit, then there exists a delta sub 1 that's greater than 0, such that for all t an element of R with 0 less than the absolute value of t minus 0 is less than delta sub 1, then the absolute value of f of t over t minus L will be less than epsilon. Okay? So what we're going to do is we're going to let delta equal to the minimum between delta sub 1 and 1 over epsilon. Okay? Then, for every t element of R with 0 less than t minus 0 less than delta, we have f of t divided by t minus L inside absolute value will be less than epsilon. Okay? Well, let's take two such t. So note, with t being equal to minus delta over 2 and t equal to, we were looking at t equal to delta over 2, these are they both satisfy that 0 less than t minus 0 is less than delta. Both of those t's satisfied because both of them are delta over 2. Which is greater than 0, we get less than delta. So let's concentrate on each one of them individually. So for t equaling to, let's start off with minus delta over 2. Okay. We have well, we have that f of t over t minus L will be less than epsilon. So that means that f of minus delta over 2 over minus delta over 2 minus L will be less than epsilon. And that says that minus 1, that's what f was of a negative number, over minus delta over 2 minus L will be less than epsilon. So that says that the absolute value of 2 over delta minus L will be less than epsilon, just simplifying that. And so using a way of translating this inequality involving absolute values as an inequality that doesn't involve absolute values, we have minus epsilon is less than 2 over delta minus L, which is less than epsilon. So here if we subtract 2 over delta, we have minus epsilon minus 2 over delta is less than minus L, which is less than epsilon minus 2 over delta. That's what we have. And then, solving for L, we get that, okay, I multiply everything by minus 1, and then I have to switch the sign of the inequality. So this says that 2 over delta minus epsilon will be less than L, which will be less than epsilon plus 2 over delta. Now, since, don't forget, delta is less than or equal to 1 over epsilon, then what we get is that epsilon is going to be less than or equal to 1 over delta. So that says that 2 epsilon is less than or equal to 2 over delta. So I'm going to replace this by something smaller. So what we have is that epsilon will be less than L, will be less than epsilon plus 2 over delta. So I just replaced that 2 over delta by something smaller than it, which is 2 epsilon, to get this result. And here's what I'm looking at. And that's what we gain by looking at t equaling to minus delta over 2. Okay, I'm almost done. Now if we look at t being equal to delta over 2, let's write it this way. Similarly, with t equal to delta over 2, here's what we get. We get that f of t over t minus L inside absolute values is less than epsilon, but this part, so how was f of t defined if we pick something that was positive? It was defined to be 0. And so this says that 0 minus L is less than epsilon. So that says that minus epsilon is less than minus L, which is less than epsilon, or that we have minus epsilon is less than L is less than epsilon. Okay. And so we have this. This is a contradiction. So this F prime of 0 does not exist. It's a real number. And that's the answer. Well, that's enough for our first lecture. I want to thank you very much for your time and patience.